Okay, so today, inshallah, we will try to finish this chapter. We were doing stoichiometry, right? And so today we are going to start with the solutions. Okay, as we know that most of the reactions in chemistry take place in solution. Why? Because the water molecules are mobile, and so when the water molecules are the ones, because of their polarity, they dissociate, or they break a compound into its component ions, and then the ions are the ones taking part in the reaction. So we all know that for a reaction, most of the reactions, not all of them, but most of the reactions, uh, require water, okay, to take place. But yes, there are a few reactions that can take place even without water, and those reactions are very few. Okay, and in those instances, the molecules are in the gaseous state, and so they but they are very few. Okay, so therefore it is very important for our calculation purposes to know either the mass of the solute or the number of moles of solute. And I hope by now everybody knows what a mole is, right? Mole is the unit that we use for the calculations in chemistry, and 1 mole has 6.02 into 10 to the power 23 molecules or atoms or ions or whatever, okay, we're talking about. Okay, so depending upon whether we are considering the mass of a solute or we are considering the number of moles of solute, we have two sorts of concentrations. Mass concentration is when we are considering the mass of solute. By mass of solute, meaning that mass in grams. Okay, usually we use the unit grams for the mass of solute divided by the whole total volume of the solution. By total volume of solution, meaning that both a solute and solvent together, the volume that they have together when they're dissolved with each other, that total volume should be the denominator. Okay, so this thing will give us mass concentration, and the units will be grams per dm cube. Dm stands for decimeter. Okay, and I think you already know that 10 centimeters is equal to 1 decimeter. Okay, okay, now if we are considering the number of moles of solute, then that quantity will be called molar concentration. Okay, molar concentration, where in the numerator you have the number of moles of solute divided by, again, the total volume of solution, both the solute and the solvent. Okay, so dm cube is the unit for volume, and mole, mol, is the unit for the number of moles. So note down that the unit for moles is mol, so we skip the last e. We don't write the last e, okay? Just mol, that's the unit for the number of moles, okay? So if you are expressing the concentration of a solution, you will use this unit, okay? Mole per dm cube, okay? And also familiarize yourself with this. 1000 cm cube is equal to 1 dm cube, and 1 dm cube is equal to 1 liter. How come? Let's talk about it a little. Now we know that 10 cm cube is equal to 1 decimeter. Deci means 10, right? You must be knowing that deci means 10. So 10 centimeters makes 1 decimeter. So 1 dm cube is actually what? 1 dm multiplied by 1 dm multiplied by 1 dm. That's why we have 3 of dm's here, because 3 dm's are getting multiplied, right? This is simple grade 7, 8 math. Now 1 dm is 10 cm. 1 dm is 10 cm. 1 dm is 10 cm. So that means 10 cm are getting multiplied with each other 3 times, and so we get 1000 cm cube. So that is why 1000 cm cube is equal to 1 dm cube. And also recognize and appreciate the fact that 1 dm cube is also equal to 1 liter. Okay, so if you get a question with liters, with the volume given in liters, don't be confused. Just convert it into dm cube. Same thing. 1 dm cube is equal to 1 liter, okay, or 1000 cm cube. Okay, so how can we calculate the number of moles using concentration? So we will talk about the molar concentration for now, okay? For example, now concentration, we all know, means how much solute is present in unit volume of solution. What does this mean? That how many moles in 1 dm cube? That's concentration. Concentration is actually number of moles in 1 unit volume. That unit volume can be liters, can be dm cube, okay, can be per 1000 cm cube or per cm cube as well, okay, whatever unit you're using. So number of moles in that unit per means 1, okay, per means 1. Per unit volume meaning in 1 unit volume, okay. So for example, now how do we calculate the number of moles given that we have concentration, that we know the concentration? If we know the concentration, how can we calculate the number of moles? If, for example, the concentration is X mole, I'm just using this variable just for explanation purposes. If, for example, we have X moles in 1 dm cube, this is what this expression means, that there are X moles in 1 dm cube of a solution. Okay, now if we want to find out the number of moles in V, now this V is again a variable for any volume of solution. So if this is the concentration given and this is the volume given, you are asked to find out the number of moles. Okay, then how would you go about it? So you know from this expression that 1 dm cube has X moles, right? Because that's what concentration is telling us, that these many moles in 1 dm cube. So V dm cube will have V multiplied by X. So V is the volume. So this is the volume of the solution. So you're multiplying the volume of the solution by the number of moles and divided by this one, which is left behind here, but that doesn't affect the final result. So you can skip this, okay, because divided by 1 is itself. So the number of moles, basically, we deduce from this that the number of moles is the product of molar concentration. Okay, this was molar concentration, remember? So we multiplied the molar concentration by the volume of the solution. So this is the formula for the number of moles using concentration and volume. So also note down that in order to calculate the number of moles in a solution, you need 2 pieces of information. You need to know the concentration, molar concentration, and you need to know the volume of solution. Okay? If you don't have any one of these, then it would be difficult for you to calculate the number of moles. If you want to find out the number of moles of a solute in a solution, you need these 2 pieces of information that you need to multiply molar concentration with the volume of solution. Okay? Now, after you multiply them, whatever your answer is, that will be the number of moles in 1 dm cube. Why? Because the volume unit that you used was dm cube. But if the question asks you to give your final answer in cm cube, then it's very easy. Whatever answer you got here was in dm cube, right? So whatever answer you got, this was in 1 dm cube, which is 1000 cm cube. And so if the answer is asking you to give answer in cm cube, you can easily find out that how many in 1 cm cube. So you simply divide whatever answer you get, you divide that by 1000. Whatever answer you get, you divide that by 1000 and you can give your answer in cm cubes. Okay, so when we will do questions, you will understand this. Okay, but But for now, just understand what I'm telling you. If you don't understand, you can raise your hand and you can ask and you can clarify your confusions. So whatever answer, so this is the number of moles in VDM cube. This is in DM cube. So if the answer asks you to give your answer in CM cube, you just divide this answer by 1000 and you will get the answer in CM cube. And the reason why we are dividing by 1000 is because 1 DM cube is equal to 1000. So these many number of moles in 1000 CM cube. So how many in 1? So you divide by 1000. I hope I'm making sense and I hope you're not confused. If you are, please raise your hand and ask right now. Is there any confusion? Okay. Now, how do we calculate the number of moles using mass concentration? Mass concentration is when we divide the mass of the solute, and of course this would be in grams, divided by the volume of solution, and this can be in DM cube or even in CM cube. So simple, first of all, we will find out the mass of the solute. If you're given the mass concentration, and again, you will need the same two pieces of information. You will need mass concentration and you will need the volume of the solution. If you multiply them, you will get the mass of solute. Then once you have the mass of solute, then the same formula, that the mass of the substance divided by the molecular mass of that substance will give you the number of moles of that substance. Okay, that are old formula that I think you must be familiar with by now. So this is how you calculate the number of moles if you have the mass concentration given in the question. Okay, is there any confusion till here? Because I don't want to move forward if you have any questions. Are we clear on this? Should I move on? You can raise your hand and then unmute yourself. Okay. Okay, good job. Now let's move on to titrations. What is titration? Does anybody know? Have we done titrations before? Can I have a piece of paper? Have we done titrations? Who knows what a titration is? Any idea? Have you guys done titration before? In grade 7, grade 8? Okay, so is there any background knowledge regarding titration? Anybody? Yes, Saad, good job. Yes,
well, it's a method of making a salt.
Okay, yes, it is. But is that the definition of titration?
No, that's probably not, but
Okay, yeah, but yes, I appreciate that you attempted the question. Yes, you are right. It is used to prepare soluble salt. That's correct. Okay, Amina?
Yes, miss, we do for neutralization we use a process of titration in which we use like acid and base, we mix them together, but we do it because we can know the exact values of the acid, the amount of acid and the amount of base used for neutralizing.
Right. Yes, you're quite there, but you're not exactly correct, but yes, you are there. So you have a vague idea of what titration is. You guys have a vague idea of what titration is. So let's brush up on that concept, okay? Titration is a method by which you find out the concentration of one substance when you know the concentration of the other substance. So basically, titration is a technique used in chemistry during a reaction between two substances, two reactants. So remember, we have two reactants, okay? The concentration of one is known and the concentration of the other is unknown, okay? Now, with the help of this known concentration, we find out the concentration of the unknown substance, okay? Now, the reactions that are commonly used for this technique are, yes, one is acid-base neutralization reaction, but that's not the only reaction for which we use titration. We can also use in redox reactions. So commonly we use titration for acid-base neutralization reactions and redox reactions. Okay, and it also involves color change because we want to know where exactly the reaction completed. Okay, now the substance, the concentration of which is known is called a titrant, and the substance, the concentration of which is unknown is called an analyte. Okay, now any one of these can be an acid, any one of these can be a base, meaning that you might be finding out the concentration of an acid, or you can be finding out the concentration of a base. Or if you are carrying out a redox titration, you can be finding out the concentration of an oxidizing agent, or you can be finding out the concentration of a reducing agent. So in case of redox titration, one is an oxidizing agent, the other is a reducing agent. Okay, but remember, what were the two pieces of information we needed to calculate the number of moles? We needed the volume of the solution and we needed the concentration, right? It could be molar concentration, it could be mass concentration, but molar concentration is easier to understand, so we will stick to molar concentration for now. So the two pieces of information that we require to calculate the number of moles is the volume of the solution and the molar concentration. If any one of these is unknown, then it's difficult, right? So therefore, if we do not know the concentration, volume should be known. And if we know the concentration, we can find out the volume. Okay, so again, we need to have a balanced chemical equation for the reaction that we are studying. With the help of that chemically balanced equation, we will find out the molar ratio in which the acid and the base are reacting with each other. So if we can find out the number of moles of one, I mean either acid or a base, using that molar ratio, we can find out the number of moles of the other reactant, right? Okay, so this is the setup. This is the laboratory setup for any titration method, for any titration technique. Okay, we have a conical flask. Now, usually, this is typically, but not always. There might be exceptions, but typically, usually, normally, this is what we do. In a conical flask, we keep the analyte. Analyte meaning the concentration of which we want to find out. The concentration of which we want to find out, so we know its volume. Okay, we take out a particular volume with the help of a pipette. Okay, and I hope you know what a pipette is and how a pipette looks like. I have shown in one of my previous classes. So with the help of pipette, we take out a predetermined volume. It can be 25 cm cube. Usually we use 25 cm cube. Usually we use 25 cm cube. We pipette 25 cm cube of the analyte out. We don't know its concentration, but we have measured out 25 cm cube of it. So we know the volume, but we don't know the concentration. We have put it in the conical flask. Okay. Now this can be an acid or this can be a base. Okay, whatever. It can be any. Okay, that is not necessary. I have seen some students learning that acid should be in the conical flask, alkali should be in the burette, or the other way around. I have seen students learning that way, but that is not true. Okay, you can have acid or base either, but the only thing that you should remember is that the unknown concentration should be in the conical flask, the concentration of which you are trying to find out, because the volume has to be known. So you pipette it out. So you use pipette for something. You use pipette when you know the volume. I have also seen people arguing with each other that no, you use pipette for the acid. Somebody says, no, you use pipette for the base. I have seen in the group students fighting on this. But remember, the thing is, you use pipette when you know exact volume. And you use a burette when you don't know how much of the volume you would need. So you keep adding dropwise till the reaction is complete. And how do you know when the reaction is complete? We use a few drops of indicator, okay? Now I will restrict my discussion to acid base. So we will use an indicator. Now that indicator will have a particular color in acid. For example, I have acid here. Okay, to keep things simple, I will keep the acid. For example, I want to find out the concentration of acid, and I am using a universal indicator. Universal indicator is red in color in acid. So of course, I added 2 to 3 drops of universal indicator into this acid, and because it was an acid, it must be red in color, right? Now I don't know how much of the alkali I need, okay, but I know its concentration. Its concentration is known. So whatever is in the burette, the concentration of that thing would be known, but the volume is not known. Volume is what I will find out, or what you will find out by carrying this experiment out. So you will keep adding the drops till, and remember, with each drop, after each drop being added, you will pick up the conical flask, you will swirl it, and you will keep it against the sunlight to look for any change in color. The reason why we are swirling is that we are giving a chance to that drop that you just added to react completely with as many molecules as it requires to. And then you're using the sunlight to be exact, because you don't want to miss the change in color of the indicator, because you don't want to miss that point where the reaction is complete. Because when the reaction is complete, the indicator will change its color. Why? Why will it change its color? Because remember, this is a neutralization reaction going on. You have an acid reacting with a base or an alkali, okay? And you will get a salt and water being formed. And remember, in a complete neutralization reaction, the salt and water are neutral in pH. So the resulting pH should be 7. And in that pH, the universal indicator should give you a green color. So don't go ahead and wait for the whole thing to turn dark green till you stop adding drops from the burette. No, you will keep swirling after each drop. You'll keep swirling. You'll keep the conical flask against the sunlight. You will look for that green tinge. It will be a very slight tinge. Don't let that tinge be missed by you, okay? Carrying this experiment out is very difficult. This was the most difficult thing in my A levels. I mean, I did everything. I mean, I prepared for my chemistry and everything. But this practical thing was on my nerves. I was like, how would I get over this? This is, practically speaking, this is very difficult, because you miss that point, you're gone. And in exams, you don't have time. So if you miss it, you will have to repeat the whole experiment. So you need a lot of practice, lots and lots of practice. Okay, with practice, you do find that point, and so you don't miss it. Okay. Okay, so the reason why we don't want to miss that point is because, why? Because we don't want any excess of the product. See, if you look at the ionic equation for a neutralization reaction, this is the ionic equation, right? This is the ionic equation for a neutralization reaction. No matter what acid you're using, no matter what alkali you use, the net ionic equation for any neutralization reaction is hydrogen ion reacting with hydroxide ion, giving you water, the pH of which is 7. And you can see that the molar ratio here is 1:1. One hydroxide can accept only 1 proton to give you 1 molecule of water. Therefore, usually when the reaction is complete between the acid and alkali, and when you have salt and water being formed, the number of moles of acid is equal to the number of mole of the alkali or the base, whatever you're using, okay? So the number of moles are equal usually, okay? And that is why you have a pH which is neutral, neutral, and that will give you green color if you're using universal indicator. Okay, so at the end point, you have only salt and water in the conical flask. You have only salt and water in the conical flask. You don't have any hydrogen or hydroxide. I mean, ideally, you shouldn't have any. Okay, and yes, Saad was correct. that these titrations are usually used to prepare a soluble salt. Why do we use this method to prepare a soluble salt? Why do we use this method to prepare a soluble salt, and why not insoluble salt? Yes? Yes, I'm waiting. Why do we use this method to use a soluble salt? Come on. Nobody? See, if you had insoluble salt, you could okay. Tayyaba, good job. Yes? Yes, Tayyaba? Yes, Tayyaba? I can't hear you. Are you talking?
The acids and the alkalis, they react together to form salts and water. So, and if the salt is soluble, it is difficult to separate from the soluble acid and alkali.
Very good. And so, yes, you are
And
correct.
it is, and it is this titration is used here to make a pure sample of the soluble salt.
Right. By pure sample, meaning that we don't want any of the reactants left over, right?
Yeah.
Right. Which school are you from?
I'm from South International School.
You're from South International?
Yes.
Okay. Okay, good job. Yes, that's right. So the reason why we're using, Jazakallah khairan. So the reason why we are using this method to prepare soluble salt is because in titration, we can exactly make out where the reaction is complete. And so we'll stop adding. And so by doing that, we're making sure that we have none of the reactants left over. Okay, like no excess hydrogen ions or no excess hydroxide ions, but only salt and water. Okay, if the salt is insoluble, it's easy to separate. You just filter out and you have the salt, and then you can evaporate, and you will have the water evaporated, and you will be left behind with pure salt. But the problem arises when the salt is soluble. Okay, so it can be dissolved in leftover reactants and we wouldn't be knowing. Therefore, we use titration, because in titration, because we use indicators and we add with the help of burette drop by drop. So all these are precautions to make sure that no excess reactant is left over. Okay, so that is why we use this particular titration technique to prepare a soluble salt, right? Okay, so okay, another thing that I want to introduce to you is that endpoint, the term endpoint indicates that point in a system where a color change occurs. Now that color change can be of the indicator if you're using one, or sometimes even the reactant themselves are colored and they change color as the reaction proceeds. So if the reactant is itself colored and it is changing its color over the course of reaction, and you can use that color change to follow the completion of the reaction, then well and good. You don't need to use an indicator, because the purpose of an indicator is to let you know where the reaction is complete. You can achieve that from any colored reactant. So if you have a colored reactant that, for example, will change its color once the reaction is complete, you don't need an indicator. No need of an indicator. In fact, it is better that you don't need an indicator, because remember, when you are preparing a soluble salt, you don't want even the indicator to be dissolved in this. Okay, if there's an indicator, there's a problem. You have a contamination in your salt preparation, right? So endpoint is where the color change occurs in a system. Now there's another term called equivalence point. Equivalence point is that point in a system where a chemical reaction is complete. It is not necessarily the same as the end point. So remember, end point has to do with color change. Equivalence point is where a reaction completes. Ideally, both of them should be equal. In an ideal situation, end point should be equal to equivalence point. Okay, but due to practical errors, due to human errors, this is not always true. Okay, so these are just terms that you should be acquainted with. Okay, equivalence point is a point where a chemical reaction completes, and end point is where the color change occurs. But you don't confuse yourself. So sometimes the end point is not, sometimes if we're using an indicator which is not changing its color exactly at the point that we want it to, so then that means in that situation the end point is not equal to the equivalence point. So we would have to change the indicator, or we should be using some other indicator, okay, in which case the endpoint should be equal to equivalence point. Okay, so I hope this is clear. If there is any question regarding this acid-base titration, please go ahead and ask me. When I was a student, I found this difficult. This titration thing, this was my weak point in chemistry, in whole chemistry. Yes, is there any question? No? Okay, let me double check if I am missing any point. Okay, so what is a titration? Who would tell me? What is a titration? Now tell me what is a titration. Yes, Saad, very good. Yes.
Titration is a method by which you are able to make a soluble salt. Acid and alkali is neutralized, so that a soluble salt can be made.
This is the same definition that you gave me before. So so there's no improvement. Come on. Titration is a technique in chemistry in which the concentration of one substance is not known and the concentration of the other is known. And so by the reaction that we know, we find out the concentration of the unknown substance. So basically we have to find out the concentration of an unknown substance, unknown concentration. We're trying to find out with the help of another reactant, the concentration of which we know. So that technique is called titration. It can be acid-base and it can be redox. Usually these are the two reactions we use for titration. Okay, you will have a lot of ATPs on this. There are many alternative to practicals on this, acid-base titration. There are two questions which come invariably every year. No ATP is complete without it. One is this, titration. The other is identification of ions. Identification of ions. That is another pain in the neck of chemistry. Okay, let's move on to the other, redox titration. Redox titrations. Okay, in redox titration, again, we are trying to find out the concentration of one when we know the concentration of the other. Okay, again, the unknown concentration's volume would be predetermined by you. You will use a pipette. Usually we take 25 cm cube of the solution, the concentration of which we know. And then we find out by the chemically balanced equation. For example, this is an example, okay, of a reaction. Okay, this is the oxidizing agent and this is the reducing agent. Okay, so we have these two reactants, and this hydrogen ion, don't be confused by that. It is only indicating that this reaction is occurring in an acidic medium. Okay, but the two reactants are here, oxidizing agent, reducing agent, and so there's a color change. So in this particular example, the oxidizing agent itself is changing color. Manganate is deep purple in color. Manganese 2+ is colorless. So we don't need an indicator here. We don't need an indicator because the reactant itself is changing its color. So when you see that the purple color is gone, so again, you will keep adding. So you will keep adding. with each drop you will swirl, and again you will keep the conical flask against the sunlight, and you will look for any changes in color. Okay, if you will see that this when you see that the deep color is completely gone, that's when you know that the reaction is complete. Okay, and also bear in mind that if one of the reactants is colored, the other should preferably be colorless. Other should preferably be colorless. And if both are colored, then that's a problem. Okay, then that's a problem, because they will mask each other, and so it would be difficult. Okay, so if, for example, both the reactants are colorless and they do not undergo any color change even after a redox reaction is complete, then you will have to use an indicator that will change its color when it gets oxidized or reduced. Okay, sometimes the reactants themselves change color when they're oxidized or reduced. In such cases, we do not need a separate indicator, but otherwise a redox indicator is used. Okay, for example, iodine solution is a redox indicator. That's an example of a redox indicator. So again, the solution, the color of the concentration of which is not known, we take a known volume of it, we pipette it out. Okay, 25 cm cube, keep it in the conical flask, and the other, and this can be oxidizing or reducing agent, doesn't matter. This can be oxidizing or reducing agent, doesn't matter. Okay, but remember, this is known volume, unknown concentration. Known volume, unknown concentration. This is known concentration, but we don't know the volume. Even if you cannot memorize analyte and titrant, it's okay. No need to learn. This is not important. What is important is that you should know the concentration of what is known, the volume of what is known. That's more important. Okay. So if you know its concentration and you can find out its volume by carrying this experiment out, so you know exactly. So at the beginning of the experiment, before you added any drop, you will note down the first reading. You will note down the first reading. And then at the completion of the reaction, when the purple color disappears, again, you will note down the reading. So that much volume, the difference between the final and the initial reading would give you the volume of permanganate that participated in this reaction. So that would be the volume of this permanganate. So you knew the concentration beforehand, and you found out the volume with the help of this experiment. And so by these two values, you can calculate the number of moles. You multiply them, you'll find out the number of moles. And if you know the molar ratio, if you have the balanced chemical equation, using that ratio, you can find out the number of moles of the other reactant. Now, once you find out the number of moles of the other reactant, you know that many moles were in this volume, because remember, you took this volume out yourself. This was 25 cm cube, for example. So you know that these many moles were in this volume. So again, you know the volume, you know the number of moles. Okay, so you can find out the concentration of this reactant. So this is how we find out the concentration of a substance, the concentration of which is unknown. So we can find out the unknown concentration. Okay. Okay. So, okay. Another thing is that this known concentration, you know, one of the reagents concentration should be known. If you don't know the concentration of both, you cannot carry this out. This known concentration solution is called a standard solution. Okay, this terminology is used in your book. Now, what is a standard solution? A standard solution is a solution which is prepared very carefully so that its concentration is known precisely. So one of the reagents concentration is known because you or somebody, or you know, the examiner prepared for you carefully, and so that its concentration is known precisely. Okay, this concentration will be provided to you in the question. Okay. Okay. So that was all regarding titrations. And so let me make a summary. This summary is given in your book. Okay, I copied it down so that it's bigger and you can see it easily, but it is there on page, this is page 170 of your book, this summary. This is very helpful. Figure 6.17. This summarizes the whole concept of titration. This summarizes the whole concept of titration, which is make standard alkali solution accurately. Now this can be any, they have just used one. This can be any, this can be acid even, you know. Okay, so make a standard alkali solution accurately so that this will be your standard solution. And so this will go in the burette. Remember, standard solution will go in the burette. Why? Because the concentration is known, volume you will find out. So only the concentration is known. This will go in the burette, standard solution. Standard solution always goes in the burette. You can remember it like that. And then pipette out the 25 cm cube of the, this should be acid. Shouldn't this be acid? Okay, to prepare 25 cm cube of alkali into a conical flask and add indicator. Okay, to prepare 25 cm cube. Okay, put acid in the burette, read the starting value, and then run acid into flask until indicator changes color. Read the final reading from the burette. Okay. Shouldn't this standard solution, this is the concentration of this is known, and so when the concentration is known, you will have to find out the volume, and so it should go in the burette, right? Yeah, I don't know what's wrong with these terminologies, but anyway, don't confuse yourself, just remember what I told you. Okay. Okay, so run acid into the flask until the indicator changes color, read the final reading from burette, and so the difference between the two readings will give you the volume of that solution that was in the burette. Then wash out the apparatus and repeat several times and take average. You should take at least 3 to 5 readings and then take their average to minimize errors. Okay. Those of you who are from other schools, Manarat, Rawad, Jawahir, and Saud International, I want to ask you, did you guys ever carry out any titration in your chemistry lab? I would be interested in knowing if you guys got a chance or even saw your teacher doing it in the lab. You can raise your hands and let me know. Tayyaba, did you ever get a chance of seeing your teachers or performing it yourself? Yes. Yes, Tayyaba, you can unmute yourself.
Miss, we just took the lesson and the teacher explained what is titration. But I don't think we did it in the lab.
Oh, you never went to the lab?
We did, but I don't think we did titration in the lab.
Oh, you have been to the lab, but you have not done titration in the lab. Oh, okay. Okay. Okay, how do you use a balanced chemical equation in calculation? So this is again a summary of how you use a balanced equation, chemical equation in calculating different things. This is a very good summary. I found this very useful. So you have reactants giving you products, right? So if you know the moles of reactant, we can find out the moles of product, or even the other way around, okay? So moles of reactant can be calculated if you're given the volume of gas. If you have gas, of course, you cannot measure its mass, so you will be measuring its volume. So you will know from the volume of gas, you can calculate the moles of reactant. If you're given a reactant in aqueous solution, then of course, using the concentration and volume, by multiplying them, you can find out the number of moles of the reactants. And if you have the reactant in solid form, you have the mass. I mean, you can divide this by the molecular mass and you will find out the moles of the reactant. So these are the different ways you can find out the number of moles depending upon the state of the reactant. Okay, gas, solid, aqueous. Now, using the molar ratio, once you have found out the moles of reactant, you can find out the moles of the product. And then you can convert those moles into the mass. If it's by multiplying it by molecular mass, you can find out the mass of the product. in case of solid, in case of gas, again, if you can calculate the mass of the product even if it's in the gaseous state by multiplying it by the molecular mass, or if the question is asking you to calculate the volume using the molar volume, you can find out the volume, and you can also find out the concentration of the product if it is in the aqueous solution, if it is in the form of aqueous solution. Okay, so this was a good summary. Again, this is from your book. Okay, now let's move on to solubility. Now, mass concentration is what we use in solubility. Okay, is there any question till now? Before I move on to solubility, is there any question regarding titration, regarding any of these concepts that we have discussed so far? Redox reactions, acid base. Okay. Now, what is solubility? Solubility is easy. Mass of solute in grams, of course, that dissolves in 100 grams of water. So notice that we are using mass for both solutes as well as solvent, right? But this is not the only way we write solubility. We can also write solubility in terms of mass of solute dissolved in volume of the solution or volume of solvent. Okay, both are correct. Okay, and also we can use the number of moles as well. We can use number of moles as well. But remember, whatever unit you're using, you have to be consistent throughout your question. Okay, so mass of solute dissolved in 100 grams of water, this is the most commonly used, or the mass of solute dissolved in 1 dm cube of solution or water. Okay. Okay, so what happens when anything dissolves? What happens when anything dissolves? Can anybody explain me in a summarized way how any solid dissolves? I have talked on this many times. Yes, Zainab? Yes, Zainab, I have unmuted you. I cannot hear you. Almost like I cannot hear. I cannot hear you. Okay, Amna?
When a solid is put into a liquid to dissolve, first of all, the bonds start breaking off and the
which bonds start breaking?
Water molecules start surrounding the particles of the solid.
Very good. Very good.
The solid molecular bonds.
Yes, yes. And are these bonds intramolecular or intermolecular?
The intermolecular.
Intra?
No, inter.
Inter, because this is a physical change. This is not a chemical reaction. Dissolving is simple physical change. And so remember, in physical changes, intermolecular. Inter means between the molecules. In between the molecules, those bonds break. So yes, Amna, you are correct that and if we're talking about a salt, then it is in between the ions. There are no molecules in salts. In ionic salts, there are no molecules. They are just ions, cations, and anions arranged together in a geometric pattern, okay, in a crystalline form. And so those ions are separated, and these ions are surrounded by the water molecules, right? So keeping that process of dissolving in mind, we understand that when anything dissolves in water, it tries to get in between the water molecules. It tries to get in between the water molecules, right? So as the temperature increases, the molecules start colliding more forcefully and they move away from each other, right? And so as the water molecules move away from each other, there's more intermolecular space. There's more space in between the water molecules within which these salts can adjust. So there's more room for these solid molecules to adjust. And so therefore, more molecules and therefore more solubility. Solubility increases with increase in temperature because there is more room in between the molecules, right? So I have discussed this many times in my previous classes. That's why I have even shown videos. I've even shown animated videos of how this process of salt dissolving in water. Okay, so greater the space in between the water molecules, more salt molecules can, accommodate and can get dissolved, and therefore solubility increases. Now, if the solute is a gas, then that's different, because gas, as I told you, they are less dense. Okay, there are no intramolecular forces of attraction between the gas molecules, though they are already very far apart from each other. And if you have any gases already in the water, and if you increase the temperature, they already are far away from each other, they are less dense. Okay, and so when you will give them further energy, they will move even farther away from each other, and so much so that they will escape. They will get so far away from each other, they will get even their density will decrease even more, they will get even less dense, and so much so that they will escape. So that is why when the temperature increases, the gases escape out, their solubility decreases. Okay, remember this. So it's not that solubility of all the substances will increase with increase in temperature. This is usually true for water soluble solids. I mean, of course, substances which are not soluble at all. Some of them do get a little soluble if you increase their temperature, but not all of them. Like sand. Sand, no matter what you do, it will never, ever, ever dissolve in water. Okay, no matter how high the temperature you raise, but the sand will never dissolve in water. It will always remain suspended, or it will settle down at the bottom. Okay. So the maximum mass of solute that can dissolve in 100 grams of water at a particular temperature will give you a saturated solution. What is a saturated solution? As the word suggests, a saturated solution is any solution in which no more solute can be dissolved in the solvent at that specific temperature. You will see it settling down at the bottom, or you will, if it's a solute, you will see it bubbling it out. Just right off, it will bubble out. It won't dissolve. Okay. So the reason why we are always mentioning temperature is because temperature affects solubility. Okay, so whenever anybody talks about a solution being saturated, or solubility of a salt, that is incomplete without the mention of temperature. Mention of temperature is very important. I mean, which temperature are you talking about? Okay, so then we plot the mass of the solute that dissolves in 100 grams of water, the maximum amount of salt that can dissolve. Maximum meaning that these lines are all saturated solutions of different substances. The mass of solubility means maximum mass of solute that dissolves in 100 grams of water at a certain temperature. So when we plot a graph of these masses of solutes dissolving in 100 grams of water against temperature in degrees Celsius, the curve or the graph that we get is called a solubility curve. So this is solubility curve of different salts. Okay, these are solubility curves of different salts. Okay, so by plotting solubility curves of different salts, we can compare their solubilities at different temperatures. Can you see? We can compare. So looking at this graph, which salt is the most soluble? Yes. Okay. Zainab?
Potassium nitrate.
Yes. And how did you decide on that?
Well, as we increase the temperature, the
Yes.
amount of the salt is also increased, which indicates that it's more soluble.
See, the solubility of even these two salts is increasing with temperature. Most of the,
that one.
yeah, but the potassium nitrate has the most. So 125, for example, 125 grams of potassium nitrate can dissolve in 100 grams of water at a temperature of 60 degrees Celsius. So, and if you compare that with potassium chloride, that's only 50. And if you compare that with sodium chloride, that's almost 40. So you can see that potassium nitrate is the most soluble here of the three, right? Right. So this is how we can use a solubility curve to compare the solubilities of different salts. And then now, if you remember the process of preparation of salt in that, remember after the insoluble salt, remember in insoluble salt, after the salt was prepared, we evaporated, right? And so, no, first we made a concentrated solution. Okay, first we made a concentrated or a saturated solution, meaning that we keep adding the solute till no more can dissolve and we maintain the temperature. So we know that the temperature is constant and we keep adding the solute till you see the solute either depositing at the bottom or floating depending upon its density. And so that's when you know that, okay, no more salt can dissolve that, because all the intermolecular space between the water molecule have been occupied. And so if you then cool it, so that was at a certain temperature. If you then cool it, then as the temperature goes down, the water molecules come close together, right? Because you are decreasing the temperature. So when you decrease the temperature, the molecules come close together. But remember, the salt molecules are in between them, but they're trying to come close. But the salt molecules are in between them, or the salt ions, I should say. To be more precise, I should be saying salt ions are in between them. So what do? They kick the salt ions out. Get out of our way. We want to get back. Okay, we want to get back. So they kick out those salt ions back, and that's when you start seeing crystallization. You start seeing crystals forming on the surface of the solution. Those crystals are the ions that have been kicked out of the water molecules because you decrease the temperature, and so the water molecules were trying to get together back, and they kicked the ions out. Okay, because there was no more space. Now the space is less. They are just out. Okay, so how can we use this to calculate how much of the salt will crystallize out? I will give you an example, and that will end our chapter, and then we will do the end of chapter questions. We will do worked examples, inshallah ta'ala, and we will also do some DVD exercises if there are any. I haven't checked the DVD yet, and we will do that in the next chemistry class. Okay, so let me finish this. So how do we, for example, I'm giving you example of potassium nitrate. So if we crystallize potassium nitrate, saturated solution, from 60 degrees Celsius to 25 degrees Celsius. So for example, we prepared a saturated solution at 60 degrees Celsius of potassium nitrate, and then I cooled it down from 60 degrees Celsius to 25 degrees Celsius, which is room temperature. So I warmed it till 60 degrees Celsius, and I added, to its saturation point, and then I cooled it back to 25 degrees Celsius. So at 25 degrees Celsius, it can accommodate only 50 grams of the salt, only 50 grams of the salt. The water can accommodate only 50. So how much will be kicked out? How much will precipitate out? We call it precipitation. The scientific term is precipitation. So how much will precipitate out? You will subtract 50 from 125. All this salt will precipitate out. So I subtracted 50 grams from 125 grams because this was what it dissolved at 60 degrees Celsius. This is how much it can handle at 25 degrees Celsius. And so the difference will come out. That will crystallize out. We called it the yield, the production of crystallization. Okay, so this is how we calculate the crystallization or the yield of different salts, okay, after crystallization. Okay, so these are the different ways how we use solubility curve. Okay, so I tried to be as fast and as precise as I could. So tell me, is there any question regarding solubility, titration, molar concentration, mass concentration, or anything, number of mole calculation, please raise your hand. No questions? Come on. No questions. Are you sure? So you understood very well. Okay. Then in the next class, we will do the end of chapter questions, DVD exercises, and if there is time, then we will also try to do past paper questions. And I will also assign questions to you guys. Okay, I will assign questions to you guys, but that will be after Eid holidays, because the next chemistry class is after Eid holidays. Okay, and please follow the schedule that I emailed you, as well as it's in the group profile picture. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh.